Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. Today we will continue with the disassembler, and if you have any questions, you can post them on Twitter or YouTube, and I'll be there to answer. So yeah, so let's go to the project. Let's open it. And let's open the debugger as well. Alright. So if I run this, we will see the same as we saw yesterday, which was the same stuff with another instruction there, which is a general purpose instruction, which there shouldn't be any problem for the disassembler because it now supports, even though it's not complete, has the basic idea how to parse opcodes for general purpose registers. So now what we like to do is just go straight on to the same place where we left off yesterday, which, if you remember, we got something left to do, which was this instruction over here. We're gonna parse another instruction now, which in this case is it's one of the special extension tables. Yeah, that's the thing we're gonna do today. So there's a special reason why we have this instruction in this case, and it's because if I compile, and if we compile, yes we do, we're gonna see that we have a problem with especially with the extension tables, and is that right now we don't have extension tables doesn't have any way to, it's pretty much the same, but I mean now we're gonna test. Before we tested an extension table entry without operands, and this is with operands. So that's the whole difference. We have to see what happens in this case, and that's pretty much it. So if we go to and just say, well, let's compile this and see what happens when we were trying to disassemble it, we can do it, and in fact I can erase this thing we got here. In fact, I can go, doesn't matter. I'm gonna say that. And well, if you think about it, well, we'll need to add it to the stream as well. And it's gonna be cross the beam resume entry. This is gonna be called add entry special. For this particular case, we do have modern present. We have rectum modern false. This is, well, we can say it, but let's say it's true, even though it's more like immediate to modern. So we're gonna have the data size invalid. This is going to be data size byte. Data size register operand size is going to be it was a byte thing. I don't remember. Let me see. It was this instruction right here, which has a byte thing, yeah. Okay. So REXR permits access to additional registers array through R15, and REXW permits or promotes the operation to 64 bits. So whenever we see, and this is important, let me just read this before anything else. So this is an instruction complement carry flag, which has opcode F5. It has, I don't know what it means, operand encoding, I don't know, 6432-bit mode, CPU ID feature flag, description complement carry flag. Okay. Instruction operand encoding, op and C0 operand, no operand 1, no operand 2, no operand trigger, not operand 4. So this tells me that there's possibly 4 operands, but there are also other instructions that have 5 operands, which are not here. Note that REX prefixes that promote legacy instructions to 64 behavior are not listed explicitly in the opcode column. Okay, so if you see here, there are two ways that the mother and byte can be used, at least let's say on the basic manner, where one is, and it happens, I mean, at least for now we have tested both of them and we have examples that represent both of them, which is one with which on which the mother represents an extension opcode, and the RM field it's a value between 0 and 7, uh, that represents a register or a memory operon. uh, and the other case is the is where the mother and byte represents two operands, one in register and one can be in a register or a memory, which is the classic case. uh, and yeah, there's also as well 1 byte, 2 byte, 4 byte, 6 byte, 8 byte, 10 byte value following the opcode. You know, this value is used to specify a code offset and possibly a new value for the code segment. So this value can be a code offset. And possibly a new value for the code segment register. So it can be an offset from the segment base. So the code offset is relative to what? To the code segment, to the IP, to the base pointer of the file, to a file pointer of the image, or it can be an absolute value. We don't know. This doesn't tell us anything about that. There's a mosquito around me. That's why I put my cap. It's it's kind of trying to access me. Okay. So yeah. So I mean, this is pretty normal. I mean, we have examples that use this kind of stuff. Uh, we assume that it's just an offset, and that's all. But yeah, I mean, it can be more than an offset. It can be an offset, and possibly a new value for the code segment register. So, but I mean, I don't know if that means like. Oh, okay, okay, okay. Yeah, I mean, we haven't seen that example, but sometimes if we want, there are instructions that allow to, uh, I don't know. Let's say we have move, I don't know, some value to the CS register, so it could probably be encoded as this thing, where we have a value that is encoded after the main or by or the motherm or whatever, and it's gonna be uh, put onto the um, let's say in this case the code segment, the code segment register. And for immediates, we know that are 1, 2, 4, or 8 by, and all words, double words, and quark words are given with the low order by first, such as little endian. A number used in floating point instructions when one of its operands is STI from the APU register stack. Okay, we have already seen that. The number I, which can range from 0 to 7, is added to the hexadecimal byte given at the left of the plus sign to form a single output byte. So let's see what the codes associated with RB, RW, RD, or RSU are. Hold me a second. I killed the mosquito. Okay, so we have these encodings byte, word, or quad word register encoded inside the main of byte. We haven't got the chance to decode one of these instructions, but it's important to do so. We have here the registers, extended registers for 64-bit mode. It needs, of course, of REXB, and just this, I don't know. I mean, I don't know what it means. If it's that it needs it, or it's that it's present. And the rec field is 0, 1, 2, 3, 4, 5, 6, 7, and then 4, 5, 6, 7. Oh, okay, so this is encoding of the rec field, but oh, okay, the rec field that is inside there. Okay, okay. So it's pretty much like, let's say 0, 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7 for DI, SI, DI, SP, BP, which is the same here, you see, SP, BP, BP, SI, DI, and then we have Okay, I got you. So the difference between encoding ch, let's say ah, to spl is that we use rexp to make the difference, you know. And for word registers we cannot do that. Well, we don't need it because we're going on words, so it's just the same. We are just repeating the entries in the table. You know, it's p. Yeah, we know it's p. It's blah blah blah. It's 4. Um, EAX is the same. You know, we have 0, 1, 2, 3, 4. This is the normal stuff. 5, 6, 7, 4, 5, 6, 7. For the quad word, in this case, we need the register RAX, RCX, RDX, RBX. We don't have anything over. We don't have. Well, yes, we do. We have RSP, RVP, RSI, RDI. The only difference is that we don't have them as in here. Okay, but the rough field is just the same, 4, 5, 6, 7. And then register codes associated with RB. Okay, this is the continuation. This for extended opcodes. R8 low is just encodable on 64-bit mode, and it's possible to get to R8 low when we have REXP and the rec field is 0. So it's pretty much like the other part of this, you know. When we have REXP, we have from 0 through to 7, and if you want to get that, you need REXP. And as well, let's say we have RE8L. So how do you make the difference between, let's say, R12L and SP, what's R12? Yeah, and SPL, since both of them need REXP. We have RAW, RAD, and we have R8. So for BX, right now we don't care about BX. We are gonna just say that we're not gonna do that for now. And this is 466, F2, F3, OF, OF3A, OF3A8, 128, 256, LIG. This is for EVX. Okay. This is a statement as it will appear in an ASM 386 program. The following is a list of the symbols used to represent operands in the instruction statements. What? Oh, okay, okay. I was like, what? Yeah, this is telling me about the ASM 386 program. It's a list used to represent operands in the instruction statements. So we have a relative address in the range from 128 bytes before the end of the instruction to 127 bytes after the end of the instruction. So that means it's a relative pointer, you know, from which is the most common case scenario. We have a relative offset that is based from the end of the instruction. And as well, we have relative 16 and relative 32. And the relative 16 symbol applies to instructions with an operand size attribute of 16 bits. That means that it can only be used when the operand size attribute is 16 bits. But is it relative to the end of the instruction as well? Or what? Because we have within the same. I mean, we know it's within the same code segment, so it's a near pointer. Let's say it can be a near pointer, or let's call it a near offset. So they got typo because the word register are RAW. I mean, word registers for extended register codes are finished with a W, and here I forgot to put it for 16. But hey. So yeah. So the immediate value, this is interesting. For example, if it's an immediate A, it's gonna be the it's a sign value between 1 minus 128 plus 127. Immediate 16 is an immediate word value used for instructions whose operand size attribute is 16 bits. This is a number between 32 minus 32,168 to 32,767 inclusive. So we say it has 65536, but yeah, it has, since it's signed value, it has to go minus 32,768 to 32,767. Between 2 million plus 2 million to minus 2 million, so to 2. But yeah, I was gonna say 2 gigabytes, but it's not gigabytes, it's just the value. We're not talking about size, we're talking about values possible to be encoded. So there we have immediate 64, immediate quad word value used for instructions whose operand size attribute is 64 bits. Okay. The value allows the use of a number between 9, oh my god, 9 million trillion I don't know how you call that, 9 quintillion and 9 quintillion. Then we have a byte operand that is either the contents of a byte general purpose register or a byte from memory. Okay, so it's a byte. So that's important because in the way that you will encode it, that means something specific, you know, because normally we will say, well, what do we want from memory? Well, you can get the address, and that would be 8. But if you want to represent the size operand, the size of the operand, you have to know it as well, and you can know it as well with the operand size attribute, which is it. By registers R8L through R15L, L are available using REX in 64-bit mode. A word general purpose register or memory operand used for instructions whose operand size attribute is 16 bits. The word general purpose registers are those: SI, DI, BP, SP, BX, DX, CX, AX. The contents of memory are found at the address provided by the effective address computation. Which is the one that we, with the combination of the scale, index, base, displacement stuff. And we know that it's a word, you know, that we get into there. Where registers are 15, right? 15 are available using our EX.R in 64-bit mode. So this is just telling us that it can be a register or memory, because that's the way the mother M is telling us about. M in this case tells us it's just a memory, 16, 32, 64, we don't know. It can be anything of them. A byte operand memory usually expresses a variable or array name. Now, for example, how do you know? This is probably because if you have operand size attributes, is the one that you use. It defines which one you choose. Usually expresses a variable or array name, or pointed to by the DS, ESI, or ESEDI registers. In 64-bit mode, is pointed to by the RSI or RDI registers. A word operand memory usually expresses the value of array name, but pointed to by the DS, ESI, or ESEDI registers. It usually is used only with the string instructions. Yeah. Okay, only for string instructions. So this is a far pointer, pretty much similar to pointer 1616, 1632, but this case probably is because it also contains 1664. The number shown with MUFs indicates its size, which is determined by the address size attribute of the instruction. So this is the special map set, which is a memory offset from the move instruction. Of type byword or double word used by some brands of the move instruction. Actual address is given by a simple offsets relative to the segment base. Look at this. This is the thing that I was looking for. It was a tricky thing because, hey, uh, um, you know, until before this, we never saw this word happen. Address size attribute was never used. That means like, well, I was like getting to the point where saying, well, um, the thing that matters normally is operand size attribute, but it depends because uh uh and what's the purpose? I mean, normally you will say, well, I mean, like for starters, we will think like, address size attributes are used just for memory addresses, or stuff like that, and operand sizes are used for actual registers, but that's not the case. Memory operands can be operands as well. They are operands. So it all depends. Because yeah, I mean, it's not totally bad, it's not totally wrong, it's just like the idea of what a pointer is and what it's not. So for example, when we're working here with offsets and we know it's a memory variable, it's a simple offset from the base segment. Here we have to take a look on the address size attribute that is currently overriding the instruction, or the effective address size attribute, and that's gonna define which offset we're gonna get. Which for the other cases, like for example, let's say we have this where we have an operand. These are the contents of memory are found at the address provided by the effective address computation. Yeah, I mean, this we use the operand size attribute for defining what in memory is the operand, because we have an operand, we are pointing towards a value, that it's in memory, but that has a specific size, which the operand size attribute is telling me what it is. The address size attribute, on the other case, it's the pointer. How we are addressing that pointer and stuff like that. So that's really important to mention, because it's like, well, what does this effective address stuff it's pointing to? So here they don't tell me about operand size attribute, but of course it's implicit. It's and that's why it's like it has been like tough to uh, make a clear cut of like to understand like, oh, now we're referring to offsets, now we're referring to pointers, now we're referring to variables, now we're referring to actual data information inside memory, actual data information in register data, actual memory. Since we have a lot of flavors in that aspect, we have to be really careful about how do we understand the thing and what are we actually talking about. Here we're talking about advertised attribute because we're looking at the pointer. We're talking at a pointer because it's not a pointer because it doesn't have the segment. Well, it has a segment which is the current segment selector, and it has an offset, so we can talk about pointer in that sense. And this pointer has a size defined by the address size attribute currently on. That's all she said. Here we're not saying like, okay, what's the size of the operand that we're talking about, but we can just assume as well that we're saying like, hey, we have an offset to a 64-bit value. The number shown with MOVs indicates its size, which is determined by the address size attribute instruction. But what does it mean? Like the address is 64 or the operand is 64? Because both of them have to be some size. It can be 64, 32, 16. Normally in 64-bit mode, the address sizes are gonna be 64. That's for reals. So on 32-bit mode, address sizes are gonna be 32. They cannot be 64. And we can have overrides and all that stuff. So as we think of offsets are thought as addresses. These are some offsets based from segment registers. When we're talking about offsets from the instruction pointer, then we're thinking about something different. It's like, okay, so it has to have also as well size. So that's the kind of thing that I'm like trying to have a clear idea of how can we handle those stuff. What's the effective address size of a pointer? Let's say it's an offset, let's say it's a far pointer, let's say it's an offset from the base, an offset from this instruction pointer, whatever. We want to know that because that's important. The segment register bit assignments are ES equals 0, CS equal a segment register. Okay. ES equals 0, CS equal 1, SS equal 2, DS equal 3, FS equal 4, and GS equal 5. So whenever we find this is that we have a 32 floating point in memory, or a 64 floating point in memory, or 80 floating point in memory, 80 bits. Tim? Yeah, wait. What? Sure. Okay. Okay, fellas. So I'll need to stop here, but we'll continue reading this spec. Because we have different, a lot of ways to encode this stuff. Well, they're not a lot, but they have important information for us about how does operands, how actually the operands are encoded, or what does it mean that a specific operand is used instead of the another, for that case. That it's the problematic thing that we like trying to find out, which is not so difficult. It's just like we're getting out to the place we're getting on to the idea of how these things are encoded. So yeah, okay, so I'm gonna put it here because this is important. And where am I? Right here. Alright, so yep, I would say please, if you have any questions, post them on Twitter or YouTube and I'll be there to answer. I would say thank you very much for coming, and yep, I think I will see you all on the next stream. Take care.